Today, I'll be demonstrating how to build a waste classification system using an IoT network. The classification models are trained on Azure's custom vision service. This solution combines both edge computing and cloud computing. The purpose of this project is to accurately classify materials as recyclable or non-recyclable using the classification model and then provide proper disposable guidance with an LLM. The system works in two stages. Firstly, edge classification happens directly on the Android device using a self-trained TensorFlow-like model that can be embedded into the application. Secondly, cloud classification happens when the image is sent to a more powerful self-trained Azure custom vision model, and then the classification results are supplemented with LLM analysis using Azure OpenAI. This is the tech stack used for the project: Android Studio, TensorFlow Lite, Azure Custom Vision, Azure OpenAI, Azure VM, and Flask. First, we need to deploy the custom vision service through the Azure portal. For this demo, I'll be using the free tier of the service, which gives limited but sufficient resources to build our project. After deploying the service, we'll access the Azure Custom Vision portal to create our first image recognition model. Since the goal is to classify material as recyclable or non-recyclable, we'll choose a classification project with a multi-class label. This means that each item will receive a single tag. Now, the training images will be set up and uploaded. I'm using a waste classification dataset from Hugging Face, which contains sorted images classified to what type of waste they belong to. The code to process the Hugging Face dataset and uploading the images to the custom vision portal is provided together with this video. When the upload is successful, each image is assigned to its corresponding text as shown. With our images uploaded and properly tagged, we will now train our edge model by clicking on the green train button. After the training is done, we will be brought to this page where we can see the model's training performance. As you can see, our model has achieved reasonable accuracy. Now we will need to export it in a format that can run on an Android device. Since we need this model to run directly on Android, we will export it as a TensorFlow-like model. This format is optimized for mobile devices. The export will give us a zip file containing two essential files: the model's TF-Lite file and a labels.txt file, which will both be used in the Android app. While our edge model provides quick initial classification, we want more accurate results for the cloud model. Therefore, we'll be using an expanded dataset from Hugging Face that has 5 times the number of images compared to the first dataset, which provides more image variations. To further improve accuracy, we'll also include the image from our first dataset. For this, we'll create another custom vision project, but this time we'll select the general A2 domain. This will ensure that the model is more powerful but requires the model to be hosted through Azure's API. The model is trained the same way, and this time we'll publish it to the endpoint of the service. We'll be using a server to host our cloud model. Therefore, an Azure VM from the free tier is provisioned on Azure portal. We will also use an SSH authentication type to connect to our VM. In order to connect to the provisioned VM, we'll click on the native SSH option, and then we'll copy the path to our private key into the text box and copy the link created. Then we'll paste it into our terminal to connect to the VM. We will create a Flask application that will be used in our virtual machine. The application will accept image uploads from our Android app, send the image to Azure Custom Vision Service API, get the classification result, use Azure OpenAI to generate recycling advice based on the classification, and finally returning the results back to the Android app. The key components of our server include an endpoint to receive images, integration with Azure Custom Vision API for classification, processing of the classification results, integration with Azure OpenAI for generating helpful recycling advice, and returning a complete response back to the mobile app. With everything set up, we'll run the server using Python 3 server.py. Our server is now running at our VM's public IP address, ready to accept requests from our Android application. For the Android application, I will not be going into the development details of the code. Instead, I will focus on demonstrating how the TensorFlow-like model is integrated and how the app connects to the Flask server for processing. The full source code of the Android application will be attached as a separate file. I added the TensorFlow-like edge processing model, model.tf-lite, and its corresponding labels.txt file into a folder named assets within the Android project, which is where the app loads them during runtime. Then, using the TensorFlow classifier class, it will process an input image by resizing into the model's expected dimensions. Then it will convert the image into a byte buffer with normalized pixel values. Next, it will feed the pre-processed image data into the model for inference, and finally return a list of predicted labels along with their confidence score. In the edge activity class, I connect to the Flask server by converting the captured image into a JPEG byte array and sending it via a HTTP post request using OKHTTP. The server processes the image and returns a classification result, which I then pass into Cloud Result Activity class for display. Now, let me demonstrate the application and its various functions. Firstly, the application is able to utilize the camera to capture and take an image, before displaying the image captured, ready to be processed by the edge classification model. Secondly, the application is able to connect to the phone's gallery and access the images stored on the phone. Therefore, a user is able to upload their photo of choice to be processed by the edge classification model. When the user is satisfied with the image uploaded, he can click on the Check Recycling button. This will send the image to the edge classification model, in which the model will categorize and give a confidence score to the user. The edge classification model has a very low latency and is able to process the image almost immediately. However, it might not be as accurate as the cloud model. Next, when the user clicks on the Cloud Processing button, the image will be sent to the Flask server for processing. This will trigger our cloud model, which was trained and uploaded on Azure Custom Vision API. The model will return the category of the item back to the user. Using the category of the item, we will pass this into an LLM prompt. This LLM prompt will be used on Azure OpenAI API, so that the LLM can tell us whether the item from this category is recyclable or not. It will also give additional info on how to recycle or dispose of it properly. To demonstrate support for multiple concurrent users, I ran the application on two devices simultaneously, each sending an image to the Flask server. The server handles these requests in parallel, confirming that multiple IoT devices can interact with the cloud service at the same time without any conflict or delay.